Right. So today we will. We were discussing about representations last time, and we began with the idea of Dynkin labels, which basically tell you about the depth of a tower. If you start from the highest weight state, then the depth of the tower along each of these simple roots. So those are given by, of course, integers, and those integers are called Dynkin labels. Okay. And we talked about fundamental representation and anti-fundamental representation. Anti-fundamental representation was, I don't know whether I have used this phrase last time, but it's the complex conjugate of the fundamental representation. Okay. So in terms in SU3, these are like what is called 3 and 3 star. So 3 and 3 star or 3 bar, etc., etc. So these, in particle physics, these correspond to quarks, and this corresponds to anti-quark. And so today we are going to talk about how in various ways how tensor products of these representations taken arbitrary number of times, arbitrary number of 3s and 3 stars. More generally for SUN, these will be like some m copies of the quark and n copies of the antiquark. So okay, so this and the Dynkin labels of this, which you can more or less figure out by Leibniz rule, that this is going to be m comma n, and if you take the complex conjugate of that, that will be n comma n, okay, because the 3s and the 3 n and the n bar, they just flip their roles. Okay. So the way we familiarized ourselves with 3 bar, okay, is by explicitly constructing that. So first we encountered that so 3 had a Dynkin label which is 1, 0, and we said that all sets of integer ordered pairs correspond to a valid irreducible representation. So therefore 0, 1 of course had to be a representation, and we explicitly constructed that 0, 1 representation, which turned out to have the property that the representation matrices for 0, 1 were the complex conjugates of the matrices for 1, 0. Okay, so that is why these are called complex representations. And today we will arrive at this 3 bar, or more generally n bar, in a different way, which is important for the subsequent discussions. So let us look at the. So we are going to discuss this tensor product representation in many ways, okay, today. Okay, so first as some kind of mixed tensors, then in terms of Dynkin labels, and then in terms of Young tableaus. Okay,
so
all of these.
M and N correspond to different colors of the quarks.
So in each of these, so for example, here itself is 1. Okay. So what does that 1 mean? It's a 3-dimensional representation. Okay. So you can think of the 3-dimensional representations as spanned by basis vectors, which are the 3 different colors. Okay. So colors, of course, are physicists' way of saying it, but it's just a three-dimensional representation. And often 1, 0, 0 is called red, and 0, 1, 0 is called blue perhaps, and 0, 0, 1 would be called green or something like that. But yeah, so it means that there are these three-dimensional representation. Indeed, those would be the colors. And when you have n square, let's say, or 3 cross 3, okay, then you can have red cross red. Okay, so let's say red. If red is the highest weight vector, then you can have red cross red. That would be the highest weight vector of the symmetric tensor product representation of 3 cross 3. We'll come to all that today. Okay, so in fact, let's do that right now. Okay. So let us look at 3 cross 3 in some more detail in a way we are already familiar with from the SU2 theory. Okay, that's what we are going to do. So this 3 representation, it has this basis vectors. This is 1, 0, 0. This is 0, 1, 0, and this is 0, 0, 1. Okay. In the particular representation of the Cartan subalgebra that we had considered, this guy, okay, turned out to be the highest weight vector. Okay, so remember that the weight diagram was something like this. Okay, and the weight corresponding to 1 fell here. So that was the rightmost. Okay, so that corresponded to the highest weight, and the corresponding eigenvector was this. Okay, so that's the highest weight vector, and that was just 1, 0, 0. Okay, so that's something that I will call 1. Okay, so then 3 cross 3 will have how many states? Of course, it will have 1, 1, 1, 2, 1, 3, etc., etc., 2, 1, 2, 2, blah, blah. Okay, so now out of these, so let me write it out once. And 3, 3. So as we discussed already, that if we want to construct an irreducible representation, okay, we should start with the highest weight vector. Okay, so this clearly will be a highest weight vector, because if you apply raising operators by Leibniz rule, it will either annihilate this one or annihilate that one, so the whole thing will be annihilated. And we'll start from here and we'll go down, okay, by using lowering operators, and whatever we get, we'll get. Okay. So this will turn out to have okay, so let me just give you the schematics. So I start from 1, 1. Now, one thing that you should remember is that this this 1 belongs to the fundamental, this highest weight vector of the fundamental representation, whose Dynkin labels are 1, 0. What does it mean? 1, 0 means if I apply the raising operator alpha 1, lowering operators of alpha 1, then what will happen? It will have a depth of order 1. Okay, and if I apply alpha 2, okay, it will be annihilated. Okay, so it can be lowered by alpha 1 only once, okay, and none at all by this thing. So if I apply now, so this is my drawing. So alpha 1 will go this way, and alpha 2 will go this way. Okay, so now this guy will give you 0. Okay, so it will not lead you anywhere. And this acted on by alpha 1, what will it do? 1, 2 plus 2, 1. Very good. So it will give you, let's say, 2, 1 plus 1, 2. Okay. Let me call it 1, 2 plus 2, 1. And we'll soon use notation anticipating Young's tableaus, in which we will call this thing 1, 2. So it's two boxes, okay, next to each other on a horizontal row, which means this is 1 and 2 symmetrized. This is just the same thing as saying this is a 1, 2 plus 2, 1. Okay. So this is the first encounter with a Young tableau that we got here. Okay. This is a symmetric representation which is coming up. Okay. So this is just a particular notation for this 1, 2 plus 2, 1 that get. All right, so that is and this is saying equal to 0, and now you apply you can apply alpha 1. Okay, so alpha 1 goes this way and alpha 2 will go that way. In case of SU2i, I didn't have any such problem. I could go straight through vertically down because I had only one simple root. Now I have two simple roots, so I have to use directions. What will happen when I apply alpha 2 to this? Somebody tell me. So what alpha 2 does to 1, we know, it annihilates. Okay. What alpha 2 does to 2, you may not remember, but it takes it to 3. Okay. So this you can work out. Okay. So we were basically always talking about the the properties of the highest weight vector. Alpha 2, this 2 is not a highest weight vector, so but you can work it out. Okay, so this will be then 1, 3 plus 3, 1. Okay, it picks up coefficients. I'm not writing coefficients here. Okay, so again, of course, this is also symmetrized. This is a generic feature which is easy to see, that if you start from a symmetric state, then since you are only applying Leibniz rule everywhere, okay, at whatever stage, whatever you get, it will be a symmetric state. Okay, so this is something that you got, which is 1, 3. Okay, now alpha 1 acting on this is what? This will be 2, 2. So both terms will give you 2, 2. Okay, so this gives you this box, which is. So you can see more or less that you are filling out boxes, okay, of one row with two boxes, okay, in some particular, according to some particular rule. Okay, the rule is going to be pretty obvious. Okay, it's a rule for symmetric tensors. Okay, what else? So this is the only example which I'm going to do in great detail. So now I have to do alpha 1 and alpha 2 again. So what will alpha 2 or alpha 1 do to this? This will give you 0 because, sorry, alpha 1, alpha 1. Alpha 1 gives you 0. What will this do? 2, 3, 3, 2, very good. So that's this box, which is 2, 3. Have we encountered 2, 3 before? No. So this, oh, I forgot to write this. This is the box 2, 2. Okay, and now I have to also do alpha 1 and alpha 2 on this guy. What will this do? So alpha 1 can act on 1. So actually it will take you to this. Okay, not a new box, but this guy. And alpha 2 acting on this gives you 0. Okay. Alpha 3, by the way, is the lowest weight vector. Okay. If you remembered from this diagram, this was 3. Okay, so that's the leftmost. Okay, so that's killed by all lowering operators. So nothing can. So now I have to just do alpha 1 and alpha 2. Alpha 1 of course annihilates it because the alpha 1 acting on 2 gives you 0 and alpha 1 acting on 3 also gives you 0. So that's 0. And alpha 2 does what? 3, 3. Very good. So I'm not writing the Kate notation, I'm directly writing the box notation. Okay. So now you see what I have got starting from 1, 1. So starting from 1, 1, okay, I have generated all the indices which are allowed for symmetric tensors. Okay. In the sense that, okay, I rub this off here, that 1, 2 I will not distinguish from 2, 1. So I will not write it separately. So when I write a box like this, it means that Ket 1, Ket 2 plus Ket 2, Ket 1. Okay. And then of course I should have 1, 3, and then I should have of course 2, 2. So 2, 1 I am not going to write, 2, 2, 2, 3 and 3, 3. Okay. So it's a 6-dimensional representation. Okay. So we arrive at the fact that 3 by 3, 3 times 3, this tensor product thing, it has a symmetric. So we began with symmetric, and of course there will also be something anti-symmetric. We'll come to that in a moment. So this is a 6-dimensional representation. This 6-dimensional representation is no wonder it is denoted by 2 horizontal boxes. Okay. Now let us look at the antisymmetric representation. So we began here 1, 1, and of course because we are generating this starting from the highest weight, okay, we just got what we got, everything is symmetric. But at this stage we missed the other possible state in the vector space. This is a 9-dimensional vector space. Okay, so clearly of course there was this guy as well. It didn't appear here, but it was there. Okay, in the full 9-dimensional vector space it was there. So now if I start from this and do the same analysis, okay, what you will get? What will you get? Sorry, that of course was the antisymmetric thing. Okay, so what you will get is that let's do this just for once. Okay, I'm not going to do this for other algebras. So we use our usual notation. Alpha 1 acting on this will give you what? 2, 2 minus 2, 2. So that's 0. Acting on this, 1, 3 minus 3, 1. Okay. So now I'll invent another notation which is just for the notation for antisymmetry, and I will call this 1, 2. This I will call 1, 3. And now I will apply alpha 1 and alpha 2 on this. So alpha 1 will do what? Alpha 1 annihilates both 1 and 3, so it is at 0. And alpha 2? 2, 3 minus 3, 1. So 2, 3 minus, sorry? Alpha 1 takes 1 to 2, so that's what it will do. Oh, excuse me. I was, thank you. So this is 2, 3 minus 3, 2, and this is 0. Thank you. Good. So this guy I will call 2, 3. Okay. And if you care about what the eigenvalue of the two Kartha subalgebra elements H1 and H2 on this R, okay, on this, what will that be? So, if the weight of 1, if the weight of 1, if the weight of 1 I call nu 1, this is nu 2 and this is nu 3. So, this is the vector. So, when I, let us say, apply H1 onto this vector, what will I get? Just apply Leibniz rule. I mean, if I act by H1 on this, so it will act by Leibniz rule, right? So, it will be H11 times 2, and so is that so it will give you nu 1 plus nu 2 eigenvalue. So, the this will be an eigenstate of H1 and it will give you nu 1 1, okay. So, let me call this so H1. So, let us do this carefully, minus 2 1. Let us act on this only, okay. So, this will give you H1 1. So, that times 2 plus 1 times H1 2. Now, H1 1 is nu 1 1, okay. So, there is an index. So, let me do I here, okay, I. So, this will be nu 1 I 1 2 plus here I will get nu 2 I 1 2 again, and of course, this, the minus sign does not matter. If you have an eigenvector, multiply this by minus 1, 3000, whatever it is, it remains an eigenvector with the same eigenvalue. So, therefore, the eigen value of this is nu 1 plus nu 2. So, this guy has an eigenvector which is nu 1 plus nu 2. And if you care to look at this thing, okay, it turns out that nu 1 plus nu 2 is, so what is the flipped thing here? So, the minuses of these things were this way, okay, were this way, whatever they are. So, and so nu 1 plus nu 2 is actually the highest weight of the 3-star representation, okay. So, I am not drawing that thing again, just check it out, okay. So, this actually is the highest weight of the 3-bar representation, okay, and then you carry through, okay, then you apply your lowering operators, etc., etc. So, therefore, we have identified the fact that this antisymmetric product of 3 and 3 is 3-bar, okay. So, that is the proof. So, we got this 3-bar. So, some kind of rule is forming about how to construct representation. So, by the way, if you have a single box, the rule here is that a single box means that it is a ket 1, it is a span ket 1, ket 2 and ket 3. For a single box, using the ket representation and the box representation is the same thing, because there is no rule about symmetrization or antisymmetrization. So, it is just that. So, single box means this, and single box times single box, we found that, so it is this plus that, this plus meaning that is a direct sum. Okay, so, this is a 6-dimensional representation. There are 3 more vectors here. It's a different representation. You add them all up, you get a 9-dimensional representation, which is what from here. So the rule here at least was that if you have originally a representation and some other representation tries to come in, this guy, you can either put it to the right or put it below up to some rules. Those rules we will specify. Okay. So this guy can join here or this guy can come here. Okay. So this is our first encounter with Young tableaus. So these things are called Young tableaus. I will give the general definition in just a moment. So this is an important realization that the 3 bar is basically this antisymmetric product of 2 3s. Similarly, it will turn out that n bar is the antisymmetric product of 2 n's, okay, etc. No, sorry, excuse me. N bar is the antisymmetric product of n minus 1 fundamental representation. Okay, so I'll make the general rules later on. So here's some exercise for you, which is to do the 3 cross to do this in this way, okay, in the Ket method. Write it out 3 cross 3 bar. So this or maybe 3 bar cross 3 is a simpler way. So you will have some 3 bar will start with 1 2 minus 2 1. That's the highest weight state of 3 bar. You must write for 3, you must write the highest weight state here. Okay, so highest weight, and then you carry on down. Okay. What you will find here is that it will be some 8-dimensional representation plus the singlet representation. This 8-dimensional representation is also the same as the adjoint representation of SU3, and this is the same as the bilinears of a quark and an anti-quark. Okay, have the same. It can have 2 kinds of objects in it. It can have a singlet, which is so this is the
So is this the 8-fold way for mesons?
Yeah, that's right. So you can have you can think of it that way also, but the same group theory also works out for gluons. Okay, so you can do it for flavor, the one that you were saying. Okay, in which if you are very old, then you would think of only 2 flavors, up and down. If you are slightly less old, then you will think of UD and S, and if you are modern, then of course you will think of all 6 quarks. But those 6 also have further one doublet, another doublet, that kind of structure. So there's a lot of interesting group theory in that. I thought that I will probably do some of this in this course, but maybe I will, maybe I should. Okay, good. Okay, so
What does that one representation correspond to?
This.
8 plus 2.
This. So if you just take the Q1 bar Q1 plus Q2 bar Q2 plus Q3 bar Q3, okay, then that's the like taking a trace, okay, and this is also this is okay. So this is an important result. So this is an invariant. This is an invariant. Why is that so? So let me write it in terms of more general mathematical notation. Okay, before that, right. So just keep this in mind at the moment that 3 bar is an antisymmetrized product of two threes. Now let me go back to this, go to this tensor objects and try to understand this 3 cross 3 bar equal to 8 plus 1 kind of result in terms of more general situations. Let us say that I call my 3 vectors as EI. This is what I was calling quarks. Okay. So, EI are my basis vectors. So, E1 for example would be that 1, E2 is 2 and E3 is 3. Okay, and the basis vectors of the 3 bar representation. So, 3 bar representation, I will not put this underline here. Okay, so imagine that this 3 is a boldface 3. I can't write boldface. So, this is boldface 3 and this is boldface 3 bar. Okay, so, this is a complex conjugate representation, and I will call these things as E bar I. Okay. These are the basis vectors of this. In fact, they are the same in terms of the physical vectors here. They are just these fellows, 1, 0, 0, etc., etc. The reason why I give them these different notations is that T acts on them, okay, differently. Okay. That is to say, the Lie algebra elements act on these guys and these guys differently, okay, because of a minus sign, okay, because of a complex conjugation which in an appropriate way will turn out to be to give a minus sign. Okay. Let's so let's prove some little results here. Is that so this is what we were almost doing the moment. So, let us act by any generator TA. This could be some of the E alphas which are like the roots, or this could be one of the Kata subalgebra elements. Okay. I act by this, in which it is understood that I is summed. Okay. Excuse me. So, this will act on that again by Leibniz rule. This acts on this fellow, and then it acts on E bar I, and plus EI. So, let me say that these are the abstract Lie algebra elements, and these are some matrices acting on I, and here I will have the complex conjugate matrices EI. Okay. This is how it acts, right. Now, this you can easily show that this up and down, okay, essentially means that, okay. So, let me do one more step. So, here this acts like that. Okay. Now, this is a transpose, and okay. So, what have I used here? I have used the fact that this TA is a Hermitian operator. So, therefore, TA is equal to TA dagger. So, therefore, and TA dagger is the same as TA star transpose. So, therefore, TA star is the same as TA transpose. Okay. So, I have used this fact, excuse me. Minus. This was the definition, wasn't it? Let me get there. Right? So, these guys, the Lie algebra elements, act on the complex conjugate representation as minus TA star. So minus TA star is the same as TA transpose. Okay, but this, so this you should do this in a sort of more detail. The way these indices appear here, you can write this object as this TA of transpose acts here. Okay, this is the transposed element, so this will act here. Okay, so therefore this will become TA EI with a minus sign and EI bar. So this second guy reduces to this. And that is 0. Okay. I mean, you can do this thing, by explicitly writing down indices and so on and so forth, which is what you should probably do. This was a little sleek trick. You shouldn't do that. Okay, you should really write this in terms of indices and blah blah. This is like T A I K E K blah blah, etc., and do it all correctly. You will get a 0. Okay. So this, so you will get a 0 here. So this guy is actually 0. Okay. There is a different way, people say these things in representation theory, which is that there is an invariant tensor, okay, in SUN, SU3 in particular, which is delta ij. Delta ij is an invariant tensor. Let me explain what this particular sentence means. Okay, so we will introduce this notation. We'll introduce this kind of notation. Now let me get rid of this. That let us consider again this 3 cross 3 bar space in which I have EI, EJ and some AIJ. And so this is a particular linear combination of these basis elements, okay, and this is some abstract tensor which is A. Now, when I transform these vectors, okay, by the Lie algebra elements, I can transport that action to these guys. Okay, so therefore, I can say that this Aij is some tensor, okay, of that of this. I mean, it's a tensor. This Aij's give you a tensor representation of the Lie algebra. Okay, and the tensor representation on the components is exactly the same as the tensor representation on the basis vectors. Okay, this is the game which we always play. Okay, in standard tensor calculus also we do that. So this is the these are called passive and active rotations and blah blah. So therefore, the fact that what I proved here is that what did I prove here? That this delta I j Ej Ei, this quantity is invariant. Okay, so therefore, this statement is meant to say that delta Ij is an invariant tensor. Okay, you say this property, you assign this property, ascribe this property to these components. Okay, so delta Ij, the tensor with components delta Ij is invariant. Okay, so you say somewhat loosely that delta Ij is an invariant tensor. Okay, that's so, but this is what it means. Similarly, there is another invariant tensor. Okay, now you know how to sort of flip between components and the real tensor. So that is epsilon ijk. So in case of SU3, it's epsilon ijk. Okay, in case of SUN, okay, it's epsilon with so many antisymmetric indices. Okay, so let's see why epsilon ijk is an invariant tensor. So we'll apply. So let us say that we want to now do this, that TA acting on epsilon, and this is, ijk can have only values 1, 2, 3. So essentially the important information is in epsilon 1, 2, 3. The other components are simply pluses or minuses of this. Okay. So let us look at TA acting on this epsilon tensor, and the 1, 2, 3 component of that. Okay. So now we know how to apply the these Lie algebra elements on a tensor. Now I will apply Leibniz rule to the indices, because think about it, this index is actually multiplying some basis vector, this index is also multiplying the second basis vector, and 3, etc. Okay. So therefore we will apply Leibniz rule simply on these indices. So what will I get? I will get 1 p epsilon p 2 3 plus TA, so epsilon 1, this will be replaced by p 3, and here I will get 2p. Please work these things out. This is how it will go. Okay. If you guys have done GR, this is how a tensor, a tensor which is a symmetric product of 3 vectors. Okay, this is how it transforms. Okay, good. And these now epsilon p23 can only be epsilon 123. It clicks only when p is equal to 1. Okay. So therefore you can replace this by 1. Here this clicks only when it is 2, and here it clicks only when it is 3. So all of these terms have a common factor which is epsilon 1, 2, 3. You can take that to be 1. So we have TA 1, 1 plus TA 2, 2 plus TA 3, 3, but that's a trace, and these are supposed to be all traceless matrices. These TA guys, they are all supposed to be traceless matrices. So therefore it is 0. Therefore, by using the Hermitianness and the tracelessness, we found 2 invariant tensors. One is delta ij and the other one is epsilon ijk. Okay, so these 2 are important concepts. Now let me go back to our, so that already tells you something interesting, which is that EI, EJ, EK, this with epsilon ijk. Okay, so the same statement made now in terms of the actual tensors, that this must be a singlet. Okay. So which in terms of Young tableaus, okay, I am already anticipating this, which will say that if you have one box, another box, another box, all of them antisymmetrized, that means what was our notation? That antisymmetrized is vertical. Okay. So this statement that this is a singlet, it does not transform. Okay. It means that if you have 3 boxes like this, that's a singlet. Okay. So 3 boxes is a singlet. It's called a singlet, or it's called a trivial representation. All eigenvalues are 0. Okay. So
does this correspond to any heteron? This singlet?
the singlet is No, no, no. No, they always have non-trivial. Wait. Depends on whether it's a thing of color that you were talking about, or yeah. If it is color, then of course, indeed, they are all color singlets. Okay, but if you are thinking of flavor, okay, then they are not. Okay, so there are two group theories going on in this game. Okay, so indeed, in terms of color, okay, a proton, neutron, all of these guys will have this property. Okay, so they will have their color singlets. Okay, but if you are thinking of the flavor group theory, then they are not.
So
okay.
There's no known particle. There's no particle at all which is a flavor singlet.
I mean, there are lots of them. I mean, the graviton, photon, you know, all.
I mean, some so there's no hadron which is a flavor singlet.
Hadron, which is a flavor singlet and a color singlet.
They have to be color singlet to compare.
Maybe you can have.
They're flavor singlet.
It is all kinds of flavor. What is it?
It's a lambda baryon, so the operator looks like this.
Oh, the UDS.
So it's an octet, right? It's a baryon octet. And in the center is the singlet.
Right.
And then, so there are two. The multiplicity is 2 there.
No, but is it with respect to UDS or is it?
UDS.
But then you know the actual thing, of course, has UDSCTB.
No, but there can be a baryon with just UDS, which is the.
No, but you were then talking about SU3 flavor theory. Yeah. Okay. So so there you are. If you consider only U, D, and S as the light quarks, then with respect to that, so that's an approximate flavor symmetry, and with respect to that, this guy is a singlet also. Right. Okay, very good. So, yeah, I mean, of course, I mean, one presumably, you know, would like to have an understanding of the, you know, chiral symmetry breaking from some more fundamental things like doing, you know, the dynamical chiral symmetry breaking, so that everybody is massless. In that case, I would have you know, all 6 flavors as massless, and then it would be and is there some singlet of that also? Maybe, I mean, I don't know. My particle physics knowledge stops here.
As you pointed out, it's only an approximate symmetry. So beyond strange quark, chiral symmetry is already the head symmetry.
Yeah.
Because quark masses are more lambda kc.
Yeah. But once I have the chiral symmetry restoration, you know, maybe one can you know, ask these questions. Okay, all right. So this is so this is a bit of I hope that I can, you know, indeed talk about some of these things in one lecture at least. Okay, all right. So good. Right. So now I can have a more general tensor. So I can have a more general tensor, which is, so now I am talking about the, again, back to 3 m times and 3 bar n times, and it will be like a I la 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 and m and j1 j2 jn and ei1 ei2 etc. EIM and EJ1, EJ2, etc. EJN, N. Good. So, right. And then again, you know, there is a particular subspace of this vector space, okay, which is an irrep obtained by taking the highest weight state of this one, and if you start from somewhere lower down, then you can have other things. So, the entire tensor product of this will have many things, okay, but there is a particular representation here, okay, which will have that state, which we kind of state that we are constructing here, namely that we take all highest weight states here, these guys, and all highest weight states here. Okay. So, in particular, in our that kind of notation, we take 1, 1, la la la, 1, and these guys are all 1, 2, 1, 2, etc. Okay. In fact, notationally, maybe I should have written the barred fellows here, okay, and the unbarred fellows here. Okay. So, let me write that particular state in the following notation, using the following notation. So, first I will write this n states, n highest weight states here, gluing them together, 1, 1, 1, 1, 2, 2, 2, 2. Okay. How many such columns are there here? N. And this, and I will glue these things together, which are these fellows. So, there are just single boxes, each containing 1, and there are m chaps here. Okay. So, this corresponds to the representation which we had called m comma n last time. Okay. So, this notation means that we have taken this particular highest weight state. Okay. Therefore, although there are many other representations in this tensor product, but by this notation we are saying that we are only talking about a particular representation. What does it mean in terms of the tensor? In terms of the tensor, we have to make sure that we take only the symmetric tensors in here as well as in here. Okay. Remember that if we start with a symmetric combination like this, go through, the symmetry remains. The symmetry remains both in this space as well as in this space. So, therefore, we must have symmetric combination. Furthermore, we also have to ensure that this guy, when any of these pairs of indices I1, J1 or I2, J2, etc., these are contracted. Okay. For any pair contracted, okay, this should give 0. Okay. So, all this is called all partial traces of this guy should be 0. So, it is a completely traceless symmetric tensor. Okay. So, in fact, you can count them. Okay. So, this is a simple combinatorics problem. So, let me just give you very briefly. So, this is some famous formula which is related to many other formulas. So, let me so how many, so let us say we are doing SU3 again. Okay. So, in case of SU3, suppose I have a symmetric tensor of m indices. Can somebody say what is the dimensionality of that vector space of a symmetric tensor with m indices in 3 dimensions? Yeah, so this. So, let us say I have some x, I1, Im. This is symmetric. there is no notion of tracelessness here because I allow traces to be defined only between up and down. Okay, so this is just symmetric. So there are m indices and each of these things can take values 1, 2 and 3. So this is the combinatoric problem. Okay. One trick to do this is that basically what should happen is that there will be a whole bunch of 1s, put a partition, then there will be a whole bunch of 2s and put a partition, and there will be a whole bunch of 3s. Okay, like that. This boils down to counting the following, that basically, so there should be n objects here overall,
Okay,
and
like,
2 partitions.
Like Bose counting.
Like Bose counting.
I see.
So think of this as n dots and 2 partitions.
So n plus
Right. So
n plus 2 factorial.
so for this counting, you don't care about how many, where are the 1s and where are the 2s and where are the 3s. Okay. Once you have put your partitions, it's automatically ensured that the guys to the left of this partition will be, you will put 1 there, between these two you will put 2 there, and here you will put 3. Okay. So do the counting only for 10 points with 2 partitions. So the answer for that is that it is this n plus 2 factorial times n plus 2 factorial, sorry, times n factorial 2 factorial. This 2 factorial is just saying that whether this partition is, is a wavy partition and this partition is a partition like that. I don't care which one is what. It's just a partition, identical partition. Identical partitions, identical points. So there's that, and then similarly there are these other indices upstairs. So you just multiply that by this. Let's say you call this thing as BNM, like this. So you do this counting now, and then you subtract the traces. What does it mean? That means that from here you have to delete all the elements in which this I1 and J1 are the same. So it's KK, J2, Jn, and I1, I2, In. The length of these strings is not the same. Okay. And if you have contracted only in any pair of places, that's equivalent to contracting anywhere because these are symmetric. So all you have to do is to delete subtract the degrees of freedom in this tensor. So you start with this. What?
That's the minimum between.
No, in any one of them, provided that there is at least.
The maximum number of traces that we can have is the minimum of.
But for counting purposes, this is the only thing that. So all the degrees of freedom here, which are of this kind, okay, you delete them. And this.
If you have KK and let's say NM, similarly.
That's all included here. At least it has a KK. So if you subtract all these degrees of freedom, then you are done. Your KK and LL, the double traces, okay, will be at least they will all be included here. Okay, so this is a kind of recursion. So what you do is that, therefore, your final answer is this. This is your final answer. The result for Nm, subtract out the result for n minus 1, m minus 1. And what you get is a famous formula. I mean, it's an SU3 is SU3 counterpart of a famous formula, which is a much more general formula. That's called Weil dimension formula. Okay, I have not done this algebra, but
Partition. When you make the partitions,
yes.
how do you know where to, how many ones are there, how many twos are there?
It doesn't matter. It's all fixed by the location of the partition. That is why the partition is just one more object like the marbles. Okay. For example, this partition could be right here, in which case there are no ones at all.
So the ones or twos are always decided from
By where the partitions are.
Yeah.
Exactly. So, right. So this is the formula. This is the formula for the dimensionality of this representation given by
This occurs in the counting of independent components of the Riemann tensor.
Indeed. Now that's slightly more involved because the symmetric properties are a little, yeah, and then there are also anti-symmetries, and so that makes life slightly. So here, excuse me.
So which formula? This is called the Weil what formula?
No, I'll come to that. I'll come to the general. So what we got here is that the dimensionality of this representation. So let me now introduce. So first of all, given a diagram like this, let us try to figure out a few things. So this belongs to 3 bar to the so whatever the notation here is that this is n and this is m. Okay, so this is 3 bar to the power n and 3 to the power m, but the irrep of that constructed in a particular way that we have said. Okay, just put the highest weights everywhere. The dimensionality of this representation is this. That is to say, the number of ways you can put your ones and twos, etc., etc. Okay, and the rule that came out while writing the highest weight state was the following: that it was all ones here, and it was 1 2 1 2 1 2 like that. Okay, so all the assignments of numbers will follow the following property. Okay, that the numbers as going to the right will be non-decreasing, meaning that it can stay put or it can increase, and then while going down it must only increase. So let me say this again. For this particular thing, okay, I have this. So as I go down along each column, the numbers are increasing. If there is a coincidence of these numbers, then that thing is 0. Okay, 1 1 appearing here means that there is a ket1 minus ket1 appearing there. Okay, so that's 0. So it must be different, and by our convention, it's only increasing this way. And here, okay, so for example, take this part. If you apply a lowering operator, we know what the lowering operator does. It changes, one of these guys to 2, okay, or this to 2, this to 2, etc. But when I apply this to 1 1 1, it takes it to 1 2 3 plus. So excuse me, 2 1 1 plus 1 2 1 plus 1 1 2. By convention, we will call this 1 1 2. Okay, so therefore there will be a thing called 1 1 2. So there is a state like that. You can carry through this analysis. Okay, people have done it for a century, and believe me that what you get is that all representations are ones. Okay, all the kets that appear here, okay, they are all represented by this rule that the numbers can stay put or increase, and this way the numbers can only increase. Okay, that's the rule. Good. And when you do that, you have counted all the kets that appear in this tensor product representation. These are the number of such things that you get. Okay, so let's work out some examples of things here. I wanted to do some proofs today. Okay, so just to familiarize ourselves with this formula. Okay, by the way, so I already said that the Dynkin label of this is m comma n, right? Because 3 appears m times, okay, and 3 bar appears n times. So 3 is 1 0, remember, that's the Dynkin label, and this is 0 1. So this becomes m comma 0, okay, and this becomes 0 comma n, okay, and then by Leibniz rule again it becomes that thing plus that, so it's m comma 0, and this is 0 comma n. You add them up, you get m comma n. So Dynkin label m comma n. In fact, more generally, you look at the number of columns of length 1, okay, and call that. So more generally, in more general situations, I wanted to do actually SU4. So let us say you have in SU4 you can have 3 columns of. Here, by the way, I should say that we have this result that as soon as you have 3 things vertically appearing in SU3, that is a singlet. So you can delete that part from the Young tableau. Okay, so that's gone. So therefore, the only non-trivial representations are all of height 2. Okay, and we know why, because everything, okay, is writable as tensor products of these. Okay, some number of 3s and some number of 3 bars. Okay, more or less we are getting towards the proof of that also. Okay, so therefore the height can be 2 and some columns of height 2 and some columns of height 1. So more generally, the number of columns of height 1, let us say that is m1, height 2 that is m2, and height 3 whatever 3 equal to m3 dot dot dot. If that is so, then the Dynkin labels are these. Okay, so m1, m2, m3, these are the Dynkin labels. So these are the Dynkin labels. Of a Young tableau. Okay. Now it's clear that, so this is m1 and this is m2, which we have called m and n. It is very easy to convert this information into number of boxes in each row. Okay, so that's called Young diagram data. Okay, so can somebody tell me how many are there in the first row? No, in general, if it is m1 and m2, so the number of boxes here are called lambda 1. Excuse me, lambda 1 and lambda 2. So lambda 1 is m1 plus m2, right? So because there are, okay, both m2 and m1 have the top row, okay, and how about in lambda 2 is that. So therefore, you have relations between the Young tableau data, okay, and so clearly from here you can see that lambda 1 must be, so M2 could be 0 of course, in which case lambda 1 and lambda 2 would be, sorry, what, M1 could be 0, M1 could be 0, in which case lambda 1 and lambda 2 would be equal, but otherwise more generally this will have to be satisfied, and of course these numbers will have to be positive like that. For more general groups, the number of boxes will keep decreasing or stay put. Okay. So good. So this is the Young data and this is the Dynkin data. That's the relation, and you can invert this relation clearly, of course, that given lambda 1 and lambda 2, you can find out that lambda 1 minus lambda 2 is equal to M1 and M2 is equal to lambda 2. Okay. I am saying this only for SU3, but in general, okay. So, so let me now say that, so there is a famous formula for the dimension of representation in terms of it's called the Weil dimension formula. I'll just write down how it goes for SU4, and next time I will say it. So what you get here, so let me write in terms of M1, M2 so that it becomes a little more. So M1, M2, what you do is to take this M1 plus 1, M2 plus 1 and M1 plus M2 plus 2 divided by 2. In case of SU4 has rank 3. Okay. I wanted to discuss SU4 quite a bit, because once you get the hang of SU4, okay, then the remaining part actually becomes rather trivial. But let me just say for the moment that SU4 has rank 3. That is clear. I think I have mentioned this. Okay, that the the tracelessness, so the diagonal. So for SU4 you can take 1 minus 1 0 0 1 0 1 minus 1 0 and 0 0 1 minus 1. You can take that. Okay. What actually Gell-Mann would take is this minus 1 0 etc. 1 1 minus 2. In Georgia's book, for example, you will find this with appropriate normalizations, and 1 1 1 minus 3. Okay. So these are the Karpov-Sablajan elements, three of them. So that's rank 3, and so therefore you will have 3 Dynkin labels for any weight. Okay. So again, it means that look at the highest weight. You have some representation. Locate the highest weight. Okay, and the highest weight vector has different depths under the lowering operators corresponding to the 3 simple roots. So there will be 3 simple roots also, just like there are 3 Karpov-Sablajan roots. So all that game you can play. There are, I mean, it's this discussion in yeah, okay, it's easy. There are no conceptual blocks here. Okay, so that this formula you can more or less guess. So it's M1 plus 1. Okay, start dictating to me. So there are M1, M2, M3. M3 plus 1. Okay, next. Look at this.
Plus M2 plus M3 plus 3.
No, first you will have these also.
Oh, I see.
M1 plus M2 plus 2. m2 plus m3 plus 2, and then m1, no, this other guy, okay, is there is no complete symmetry between m1, m2 and m3, okay. So this m2 is something special, okay. So m1 plus m3 does not appear. So the next guy, so the middle fellows, so you only have the, you know, the 1, 2, 2, 3, 3, 4, etc., that combination, and this, okay, and divided by 12, okay. So I'll say the more general thing is, you know, today I wanted to say this in detail because I had SU4 in mind, but so let me also write down while I'm at it. So I don't have the formula for the general SUN here, but next time I will write down the general SUN formula including this denominator. But let me tell you the general dimension, another general dimension formula, which is equivalent to this, of course, which I am writing here for any SUN. So that is the following. Okay, so as I said, the Dynkin data can be transcribed to Young data. Now this is for general thing. This is given by lambda I minus lambda j plus j minus I divided by j minus I. This sign is bothering me. It should be probably, it should probably be strictly less than the thing. So, well, okay, I don't have the source here, but yeah, okay, this could be strict inequality here. All right, so there's a formula in terms of the Young data, and this is what people use most of the time. There is also some, you know,
otherwise sometimes
it could be some 0 by 0 thing. Yeah. So let me correct it. Let me correct it. It could be 0 by 0, but you know these are all integers. There are no limiting procedures here, so you can't use L'Hopital's rule with integers. So, okay, so this I will correct, and there is also another representation of this, okay, in terms of what are called hook lengths, okay. So that's another thing which is that the no, let me not get into that. I mean this formula for now. This formula for now will do for us. So this is the SU4 formula, that's for sure, and this is the general formula. I'll also write down the equivalent formula for Dynkin labels next time, and presumably there is a strict inequality. Let me get to the points that let me work out some. You know, after all this, we should be able to work out some things. Okay, or understand. Yes.
This is the maximum dimension, means the dimension of the
let's work out some things. After all this technology, you should be able to work out some simple tensor product decompositions. So this is the one in which I start from the as I said, let us say in SU3. Okay, in case of this, there will be an understanding that I take these many threes and these many 3 bars. Sorry, these many 4s and these many 4 bars, and there's also, so the 4 bar is an antisymmetric product of 3 fundamentals, 4s, and then there's also an antisymmetric of 2 4 guys. Okay, that's a 6-dimensional representation. So basically, a convenient basis for finding all representations is to take some number of 4s, some number of 4 bars, and some number of 6s. Okay. So the 4s will correspond to just box, 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 etc. The 4 bars will correspond to 3 horizontal gluing of boxes of the heights 3, and the 6s will correspond to horizontal gluing of boxes of height 2. Okay. So as a result, you will have a Young diagram, okay, which is given in terms of, in other words, again the Dynkin labels M1, M2, M3, okay, will measure how many 4s are there, how many 6s are there, and how many 4 bars are there, and it will translate to clearly Young tableau the way I just said it. Probably I said it too fast, but this is how it happens. Okay, so let's work out some things. Okay, let's try to prove this again. Now, without doing any of the Klebs-Gordon chasing through the kets. Let's prove this. Okay. So as I said, this for SU3. Okay, meaning that this rule we will take. Okay, namely a new box can join here and join here. We will go to more and more complicated examples to understand this rule really. Okay, so we'll do this, and now there will be this and this. This is just to say where the new box is. Once I have done that, I will remove the shading. Okay, so I get therefore the formula. Now let's work out the dimensionalities by using this. Okay, so what are the M1, M2 values for this? Remember what M1 is. M1 is the number of columns of height 1, and M2 is the number of columns of height 2. So therefore, this is 2, 0. And how about this? 0, 1. So indeed, this is the anti-fundamental representation. So therefore, this has to be 0, 1. This we knew already. But now, with our new knowledge of M1, M2, we can be more confident. Now, let's apply the Weil dimension formula. Okay. So, what is the dimensionality of this? So, what we are supposed to do is to take 2 and add 1, take 0 and add 1, and take 2 plus 0 and add 2, and divide by 2. Okay. So, what do we get? 3, 1, 4, divided by 2 is 6 indeed. But of course, this one we explicitly constructed all the kets. So this has to be 6-dimensional representation. So Weil is correct. Okay. This again, let us do this. Okay, is 0, 1. So the dimension would be 0 plus 1, 1 plus 1, 0 plus 1 plus 2 divided by 2. So it is 1, 2, 3 divided by 2, so that's 3. So we got 3 cross 3 is equal to 6 plus 3. It doesn't tell you that this is 3 bar. For that, you have to do some extra work. This only tells you the dimensionality of the representation, but the fact that the Dynkin label here is 0, 1, that tells you that it's an anti-fundamental representation. Very good. Let's do something else. Let's do something more. So let us do 3 cross 3 bar. So now we'll do 3 cross 3 bar. Okay. So which we'll write as 3 bar cross 3 for convenience. 3 bar cross 3. Okay. 3 bar cross 3. So what's 3 bar? This is 3 bar, and cross what's 3? That's a single box. Okay. If I was giving some PowerPoint presentation, you know, it will come to me like that and like this. You know. Okay. So what are the possibilities? That let's do. This is a possibility. Our convention, remember, is that as we go towards the right, okay, the heights should decrease. Okay. Good. So therefore, I cannot stick it in here. Okay, because then you know I have well, basically I don't allow that. Okay, why? Because suppose I just do this. Okay, my primary rule is that the number of boxes as I go down should decrease. Okay, so here the number of boxes here in the horizontal row is 1. Here it's 2. That cannot happen. Okay, 1, 2, you know, things staying the same or decreasing is okay. Increasing is not okay. So this is not allowed. Where else can it go? Down here.
But that's 0.
But that's the singlet. Okay. So therefore this is the same as the singlet representation, the one-dimensional representation which has all eigenvalues 0 by all the Lie algebra elements. So therefore we get this plus 1. Now what is this? Let us look at the M1, M2 values of this one. 1, 1. Good. So this is M1, M2 is 1, 1. Dynkin label is 1, 1. So 1 plus 1, 1 plus 1, 1 plus 1 plus 2 divided by 2. So that's 2, 2, 4 divided by 2. So that's 8. So indeed this is 8. So that's the we also happen to know independently that this 8 is also the dimensionality of the adjoint representation. And if you just stare at it a little bit more, it is the adjoint representation. Let's do something more challenging. Here it is, 8 cross 8. Okay, so now we are getting ambitious. So that's the last thing that we will do today, 8 cross 8. Okay, now by now you guys should tell me what to do basically. So this is how 8 looks, and I have to do 8 cross 8. So these are new things coming. So suggestions here. If you really think in terms of kets and stuff, symmetrize, anti-symmetrize, etc., you can derive the rule yourself. I assure you, I am not kidding. Okay. But here, yes.
We just the bottom thing we just move it to left, perhaps. And so that we have.
There are many possibilities now. Okay. So first of all, some things I have to say, which is that let's name the top row and the bottom row differently. Okay. Let's label these things as A and let's label these things as B. And we ignore B for the moment and see how to stick these A's to these things by allowing these things to split. I think of these A's as two independent boxes, okay, and I allow them to split with a certain rule. So, first I allow this these A's as two independent boxes and to join anywhere that it likes up to the restriction that it has to be a Young diagram. Okay. So, tell me what all can happen. So, this is the thing upper, yes, and what about the second A?
It can
Also there, good, so that is one possibility. Then,
Form a complete square.
so let us go in steps. Okay. So, have we exhausted the top row possibility? One can come still in the top row, and the second one can go here or here. In both cases, it is a valid Young diagram. This, and then again still sticking to the top row possibility, it is here. Okay. So, now we have exhausted the top row possibility. Now, we stick into the bottom row, the second row. Okay. So, now I can't put both of them here because that is not a valid Young diagram. So, A is here and I can't put the second A here, that is also not a valid Young diagram. Okay. But I can put the second A here, this is a valid Young diagram. Okay. So, after doing this, we remember that we have not dealt with B. One more possibility, have I missed something? Both A's below, yes, that is possible, but both A's below would be, so first of all this already has three things here. So, basically this actually is equivalent to just two guys here. So, this is equivalent to two guys here. I still keep this here in this way to sort of recall the origin of how this happens, but you do not allow 4, you allow up to 3. Anything that looks like having a 4, that is taken to be 0. You delete that representation. Here you do not delete this representation, you just say that anywhere a height of 3 appears, okay, that is a singlet and you can erase it. Okay. Not the whole thing, erase only that column, okay. That is the rule. But 4 you actually erase the whole thing, okay, because basically there's a factor of 0 in that thing. Okay, good. Now there is still B, okay.
I think the anti-symmetry and symmetry part will justify that, because previously A are both symmetric, but if you put in the final diagram both A up and down, they become anti-symmetric.
Okay, good point. That is also another. That is also indeed another thing, that the two A's together. So here clearly there is one option in which you could put 1 and 1. Okay. So this thing not quite. This AA does not mean that these are values, value as 1. There is a possible Young diagram like that. Okay.
So,
and
for example, if I consider
Yes, indeed, indeed you can, right. I mean, this A is just a sort of notation which says that, but it can it can flip its nature from horizontal to thing. It's okay. Now now about B. So this is the so far we have not done anything new. We have done exactly what we have been doing before. Okay. So far as the A guys are concerned. Now the B. There is some new element that comes in here. Okay, where all can B go?
Below A.
So for instance, B could come here, okay, but there is some strange rule which says that
I think here the argument will work like
The
A and B
antisymmetry.
is antisymmetric.
Yes.
The
So
antisymmetry has
that's
to
why
be
you
respected.
can't put B beside A.
yes, I think that presumably is can be worked out. Let's see. So I could only have, what are the numbers that could go in here? 1, 2, minus 2, 1. 1, 2, minus 2, 1. Yeah, I think here probably it will work out that way. Let me tell you what the rule is. The rule is that so you cannot put B here, because when you scan these boxes, okay, in the top row you start scanning like this. By the time you encounter a B, you should have encountered at least those many A's, those many or more A's. Okay. So if you first encounter a B here, this is a disallowed diagram. Okay. If it was like some B here and you have encountered already 2 A's, then that's an allowed diagram. By scanning from right to left and then from top to bottom, you should encounter more A's, okay, than B's, more or equal number of A's than B's. Okay.
Independently, left to right, right to left. And
No, so what you should do is to so you should scan first row first, and then the second row, etc., etc. Now the number of A's that you have counted, okay, should exceed or equal to be equal to the number of B's. Okay, if the number of A's is too few, okay, that's not a valid. So let me say what are the
number of A's before B, right?
number of A's before B. Okay, in this kind of a thing, you count the top row, then you count the second row, etc., etc. Okay, it's a funny rule, and okay. So the first thing that you can do is this, because here you have scanned the first row, you got 2 A's. Okay. Now you count the scan the second row from the right. Okay, you have encountered your B, but by this time you already have counted 2 A's, so that's okay. Okay, good. And
So we don't scan vertically at all.
no. We scan rows, and then we go like in rows, in the space of rows we do this. Now with the same configuration, there is another possibility, of course, which is the following. And remember that this is where this guy was, and here you could put it here. That is also okay, because you do this, you have counted 2 A's, so this one is a valid diagram. So this is okay, this is okay. All right. Now with this, okay, what are the possibilities that you can have? Again, you can't stick a B here. You can stick a B here. Okay, you can stick a B here. That's okay, because as you scan this, you have counted 1 A. Okay, and you have started scanning here. You can encounter a B, but that's not a problem because you already have 1 A here. Okay, and with this configuration, do you have something else? Yes, you do. And you can have a B here. That's also okay. 1, 2, and you encounter a B. So it's fine. Good. Now, if there are more B's, you know, with just one B, of course, all you have to ensure is that by the time you have encountered your B, okay, you should have encountered an A. Okay, but with more B's, you know, the fun becomes more. Okay, because okay, now all right. So that's this. With this again, you know, you can have a B here or a B here. Sorry, only a B here. Only B here. So what are the possibilities that I got? I got this, and then and I had this guy. No, this was this. So that's no. This is you take out the singlet part. Then this is singlet times an anti fundamental. Hold on.
That column, there are two elements. So if I stick a B at the bottom of it, we'll again end up with a singlet. Wouldn't be?
Here? Yeah. So if I have a B here, that would be a singlet indeed. Correct. I'm missing something. Hold on. What was my other A configuration? I rubbed off something here. So I have got this. I have got that. Yeah, I'm going to look at this. AAB, yeah. And then A. So here I have another possibility, which is okay, ABA and AAB, yeah, ABA and AAB, and that's it. I have not missed anything else. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Correct. Now, the last thing that I'll do is to work out the dimensionalities. But by now, you know, you know how to do these things, and so what you have here is that, oh gosh, I forgot to write the dimensions in this note. One of these things becomes a.
No, they become the last thing will be 1. And
so this guy is 8 clearly. So this is an 8. Here is another 8. So 8 appears twice in different ways. And this guy, let's work it out. It's not a big deal.
the last thing
So
will be 1, right?
what? Last thing is 1. And this here is that the 0, 3. Okay, so that's 0 plus 1, 3 plus 1 plus 0 plus 3 plus 2 divided by 2. What is this?
10.
That's 10. Good.
Why are you using this formula? Only M1 and 2. There are three
That's a SU3.
No, I'm still doing SU3. So the number of columns of height 2 are 3, and there are no columns of height 1. So no columns of height 1 would say 0.
But in the second, the next thing, there is a column of height 3.
That's a singlet.
Oh yeah. So you forget about this. So whenever a column of height 3 appears, okay, you just you know, cross that out. Okay. So therefore now it will be the old guy, you know, this way that's a 1 comma 1 represented, that's 8, and again here also you do that, so that's this, and here there are 2 such fellows. So all go away, okay, singlet times singlet, so you just have a singlet. Okay. So you just have a singlet, this, and this is 10, so that fellow is 10, and this I think is 27. Ah, yeah, it is. Let's work it out. So what is this again? So this is 2 comma 2, right? 2 comma 2. So 2 plus 1, 2 plus 1, 2 plus 2 plus 2 divided by 2. So 3, 3, 6, 2. So that's 27.
So the last thing is 10.
27, and that is 10. So therefore we arrive at the tensor product decomposition, which is 8 cross 8 is 27 plus 10 plus 8 plus 8 plus 1. Of course, you should check that the whole thing becomes 64.
Another 10, yeah. There will be 2 10s.
Oh, I have?
No, that thing is.
Oh, I rubbed off something?
The first diagram here, the peak would be in the bottom. That diagram gives you another 3 comma 0.
Oh, the stuff here?
Yeah.
Uh-huh. I see. That is correct. I see, okay. Like that, let's say. Now have we got 64?
Yes.
Okay, very good. 28 plus 48 here and 16. That's 64. Very good. Okay, so that's the thing. So now, you know, I'll leave this, Jesus Christ, I will leave this as an assignment to do the SU4 case, which is really straightforward. Yes?
For SU4, you have written the general formula for getting the dimension. So I think if we can interchange M1, M2, we will have different diagram but with same dimension. So do we write both as same or some other? So how do we?
Oh, you mean that when do I see that there is a complex conjugate thing? No, dimensions are not the real story. The real story are the Dynkin labels. So, you know, they use funny symbols like, you know, 10 prime, this, that, and so on and so forth. You know, when people didn't know that much about the group theory, they thought that dimensions are all. So everything was written in terms of dimensions. So like this. So here, you know, sometimes you may see some tensor product decomposition like 10 plus 10 prime, you know, things like that. Yeah. So you use this prime kind of stuff when the Dynkin labels are different. Of course, sometimes the Dynkin labels could be just the complex conjugates. Okay, so that's like the left-right symmetry of this thing. Last time there was a question in SU4. What happens if you have something like this, 0, 1, 0? Okay. This actually, you know, you might think that the complex conjugate of this is itself. It's actually true. It's a real representation. Okay. This is a 6-dimensional representation. It's a real representation, and there's a cute trick of finding complex conjugate representation of a Young tableau. Okay. So let me just tell you that. That's the following. That suppose that you have, it just follows by interchanging this M1, M2, M3 to M3, M2, M1, or if you have more stuff, you know, you just, so it's like that. So if you have, let us say that some Young tableau, whatever, something, something like that. And you could go up to, let's say, 5 or 6 or whatever it is. So let us say SUN. SUN. So what you do is to replace the first guy. Okay, so let's say this is some column length, whatever it is. So you replace this by n minus that. Okay, so you write n minus 3 things here. Okay, so let us say I'm doing SU4. Let us say I'm doing SU4. Complex conjugate representation of this would be given by the following idea, that a column of height 3 is replaced by a column of height 1. 2 is replaced by 2. And 1 is replaced by 3. And in order to make this a valid Young tableau, you just flip it around the vertical axis. So basically this will become this way, 3 and 2 and 1. So this particular representation turns out to be real representation. Okay. 0, 1, 0, we can already see that it's a real representation in the following way. So what is 0, 1, 0? It should have no columns of height 1 or 3, but it should have one column of height 1. So now it's obvious. So I have this, and the bar of that is replace this by a column of height 2, which is itself. Therefore, this is equal to that. Let us also try to find out, about the anti-quarks in SU3. Okay, single box representation of that is this, which is something that we have painstakingly derived previously. Okay, and similarly, if you want the bar of this, that of course is that. Okay. No, this will not take you from the adjoint to fundamental. However, if you want to know that, okay, so how a quark anti-quark bilinear can give you some gluonic representation or mesonic representation, then you may, and you have forgotten how the anti-quark looks like. Then what you do is to do this trick to get the anti-quark, and then do your Young tableau thing, and then the first thing that will come to hit you is that the box sticks in here, so you get your adjoint representation. So a lot of tricks are available in the literature. Of course, this has to do with, so there is a beautiful geometry of all this. That's called Weil reflection and reflection. There's a geometry of the root space and the weight space and so on and so forth. So a lot of these stuff, they actually owe their origin to the beautiful geometry of the space of Lie algebras. But I wouldn't have time to do that in this course. So next time, I'm nearly at the end of what I wanted to do about representation theory. Maybe I'll just mention a few things about SO groups, in particular Clifford algebra and spinors and so on, and a little bit of finally some physics application. Okay, so that's next week. I have some again. I have some possible conflict of the time slot with my Tuesday lecture, in which case, unfortunately, it will be Friday again. Okay, and probably that will be the last lecture on group theory, and after that, after a break of a month or so, I'll start topology. So So there will be some perhaps 3 lectures or something on topology. Okay. So no, I think group theory is either well, maybe I don't know. Yeah. So I'm hoping that I can take both lectures next time, so I can at least give some glimpses of. Maybe I'll not do any formal stuff anymore. Okay. So you can read up the SO representations from Georgia's book, and I'll give some. So today's stuff, the SU4 counterpart of whatever I did. Okay. Please work that out. I'm not formally placing these things as an assignment, but take this, you know what to do. You try to find out the Karthasar algebra, the way I said, the roots, and I mean it's more or less all spelt out in Georgia's book for general N. But if you work it out, then you will see some, you'll have some more sort of facility with these things. So next time, either on Tuesday and Tuesday, Friday, or at least on Friday, we will discuss a whole lot of physics examples, giving basically the links to how these things grow. Okay, particle physics examples and maybe some other examples which also appear in. Yeah, I think I should mention a little bit of the spinors. Maybe I'll do that also. Okay. All right.